So the first RC circuit we're going to look at is what's known as a series RC circuit. And as we emphasized in the last section, this circuit is simple enough that we'll be able to figure out what's going on with the current in the circuit, the voltage across the elements, and the charge on the capacitor as a function of time. So my series RC circuit basically says I'm going to take a battery that has a voltage of V, a resistor that has a resistance of R, a capacitor that has a capacitance of C, and I'm going to connect all three of those things in series with each other. And then I've got a switch here that I'll be able to close as I start my clock at t equals 0. So one thing I'm going to emphasize right up front, because some things will vary with this circuit and some things won't, what we're going to try and do is use capitalized versus lowercase letters to help us think about things that are changing and things that aren't. So notice V, R, and C are all capital letters. These things won't change. The voltage of the battery will remain the same. The resistance of the resistor will remain the same. The capacitance of the capacitor will remain the same. All three of these things will remain the same regardless of what's going on with our circuit. When we close the circuit at t equals 0, initially the capacitor acts like a wire. And so what that means is you basically just have a battery and a resistor. This is a complete wire sort of running down the right hand side of the circuit. This is a complete wire because we've closed our switch. And so at that initial instant when we close the switch, we're going to start to get current flow. The circuit will behave as if there's just a battery in series with a resistor. Once that current begins to flow, it's of course going to start to build up charge on the capacitor. So we'll have a positively charged plate that's connected to the positive terminal of the battery. We'll have a negatively charged plate that's connected to the negative terminal of the battery. And charge will build up. And as that charge builds up, what's going to happen is the capacitor will start to act like a second battery that is trying to drive current in the opposite direction. So you've got positive terminal, negative terminal of the battery. They're trying to drive current clockwise. As the capacitor builds up charge, positive plate on top, negative plate on bottom, it is going to act increasingly like a battery that generates what's known as a back EMF that will try and drive current back in the other direction. So what that means is the back EMF is going to reduce the current in the circuit. And this particular function that describes how the current decays within our circuit is given here at the bottom of the screen. So this is saying that the current as a function of time, and again, the current changes in the circuit, which is why we're using a lowercase I here. The current as a function of time, not multiplied by time, but as a function of time, is equal to the initial current in the circuit. Again, that's some value that doesn't change, times this exponentially decaying function, e to the negative t over RC. Time changes, R and C do not. The resistance of the resistor stays the same. The capacitance of the capacitor stays the same. So if we want to figure out what this value I naught is, what's the initial value of the current at the instant we close the switch? Well, again, we know that at t equals 0, the capacitor is going to act like a wire. So when we close the switch, our series RC circuit behaves like this one. So it basically behaves like just a battery and a resistor connected in series, because the capacitor, at the instant we close the switch, the capacitor acts like a wire and the switch now completes a wire. Well, we can use the loop rule to figure out what's going on in this circuit at that instant of time. So obviously whatever voltage I gain across the battery, I've got to drop across the resistor. And again, the voltage of the resistor will change, which is why I'm using a lowercase v here. The uppercase V is still the voltage of the battery. That doesn't change. At t equals 0, those are the only two elements that are contributing in my loop rule. And of course, I know that the voltage of the resistor I can calculate as the current flowing across the resistor that's I naught at the instant I close the wire, times the resistance of the resistor, that's R. And so this is easy enough to solve, and I get that that initial value of the current is simply going to be equal to the voltage of the battery divided by the resistance of the resistor. And so I can put that into my equation, and what I get is the current as a function of time is equal to the voltage of the battery over the resistance of the resistor times my decaying exponential, e to the minus t over RC. There's a couple things that we can do with this. One, of course, is that we can plot it out. And so we know that this function is going to start at its maximum value of V over R and then decay away. So the current will decay within my circuit. There is a special value of the time that it's worth paying attention to. So if I choose to define what's known as the capacitive time constant. So the time constant gets tau because this is the one we're going to use in our RC circuits with a capacitor. We'll sometimes use the subscript C. If I define the time constant as equal to RC, what I can do is plug that in, and so I get that the current as a function of time is equal to V over R times e to the minus t over tau. That means that there is this special point in time where I look at the time equal to tau, so a time of one time constant. So this becomes e to the negative 1, and that will tell me interesting information about what's going on with the circuit. So there are three sort of points in time that we're going to think about when we think about these parameters that are changing. And so we'll start by thinking about the current because we know it's going to decay. Initially, at t equals 0, the current through the resistor is equal to V over R. It's at its maximum value. At one time constant, notice that it has already fallen off to the point where this is e to the negative 1, that's 1 over e, which is basically 0.368, so the current will have fallen off to 36.8% of its initial value after one time constant. Roughly speaking, after one time constant, the current will have dropped to about 1/3 of its initial value. As you let time increase, so it goes to 2 time constants, 3 times constants, 4 times constant, 5 time constants, keeps on going, as it approaches infinity, basically if you wait long enough, once you've gone to 5 or 6 multiples of the time constant, that qualifies as long enough. Anything past that, you've waited long enough that you can treat t as if it's gone to infinity. No current is left flowing through your circuit. So again, our current decays away to nothing, and it does it basically within about 5 time constants. So it drops about 2/3 in the first time constant and then slowly decays away the rest of it over the next 4 or 5. So that's what's going on with the current. Well, now that we know what's going on with the current, we can think about what's happening with the voltage across the resistor as our capacitor is charging. I know I calculate the voltage across the resistor as current across the resistor times the resistance of the resistor. And again, that I is what we've just calculated out, so I know what to plug in. So I've got V over R times my exponential decay term times R. The R's obviously cancel out, and so I see that the voltage across the resistor is equal to the voltage of the battery, that's big V, times this exponential decay term. And so I can plot that out, and again what I see is at t equals 0, the voltage across the resistor is at its maximum. But it will also decay just like the current. And in fact, it's decaying precisely because the current is decaying. After one time constant, the voltage across the resistor is down to 36.8% of its initial value. And then when you wait long enough, as t approaches infinity, the voltage across the resistor drops to 0. So what that tells me is as the current basically drops to 0, there is no voltage drop across this resistor. Once the capacitor becomes fully charged, no current still flows through the circuit because the capacitor basically acts like a battery that's driving current back against what the direction the battery is driving it The back EMF cancels out the EMF of the battery. There's no current left in the circuit. That's when I have my fully charged capacitor. Well, of course, I can think about the voltage across the capacitor as it's charging. That will also change just like the voltage across the resistor. So as more and more charge builds up on the capacitor, its voltage will increase. After t equals 0, I have 3 terms in my loop rule, because now once charge starts to accumulate on the capacitor, it also has some voltage. So I can solve for the voltage across the capacitor. It's just going to be the voltage of the battery minus the voltage drop across the resistor. Well, I know how to calculate that out. I plug in for I, and so what I end up getting is that the voltage across the capacitor is equal to the voltage of the battery. That's still the big V out front, but now instead of just being times that exponential decay term, it's times 1 minus e to the minus t over RC. And so this tells me that voltage across the capacitor behaves differently than the voltage across the resistor. So the voltage across the capacitor starts at 0. Again, if there's no charge built up on the capacitor, then there's no voltage drop across the capacitor. But once I get to one time constant, the voltage across the capacitor has increased to 63.2% of what it will end up being at the end. And of course, at the end, it will be equal to the voltage of the battery. When my capacitor is fully charged, there's no current in the circuit anymore, which means now my loop rule basically says that the voltage, whatever I gain across the battery, there's nothing to drop across the resistor because there's no current going through the resistor, so it doesn't have a voltage drop. And I've got to drop everything across the capacitor, which is why once I have a fully charged capacitor, its voltage is equal to the voltage of the battery. So you can see that as the voltage across the resistor decreases, the voltage across the capacitor increases, and when I add those two things together, I still get back the voltage of the battery. The voltage across these two elements has still got to be equal to the voltage provided by the battery. Well, if I want to think about the charge sitting on the capacitor, again, that's going to change as a function of time. So it's going to be Q, here it's little q because it changes, equals to C times the voltage of the capacitor. So again, this is my fundamental relation for a capacitor. It's just that two of these parameters are changing, the charge on the capacitor and the voltage across the capacitor, the voltage between the plates. The capacitance of the capacitor is not. I'm not doing anything to change the geometry of my capacitor. When I plug in what the voltage of the capacitor is, basically that just says take C, multiply it times V times 1 minus e to the minus t over RC. And so again, what I see here is that the charge on the capacitor grows, which is what I expect since I know that I'm charging my capacitor in my circuit. Again, it starts at 0. There's no charge on the capacitor at the instant I close the circuit. After one time constant, that charge is up to 63.2% of what will be its final value, and then its final value, as t approaches infinity, ends up being equal to C times V. So the capacitor of the capacitance times the voltage of the battery. So what this means, of course, is that once the capacitor becomes fully charged, it will have a charge of C times V sitting on those plates. So let's summarize all of this. Again, here's my circuit that I've got to charge my capacitor. I know that at any point in time, my loop rule tells me that the voltage of the battery has got to be equal to the voltage drop across each of the two other components in my circuit. So the voltage drop across the resistor plus the voltage drop across the capacitor, and again that's a voltage drop across the capacitor because it's generating a back EMF. And I know how to calculate those things. The voltage across the resistor is going to vary because the current varies. The voltage across the capacitor is going to vary because the charge on the plates vary. The functions that describe how each of those parameters change are given by the following equation. So the current as a function of time is V over R times e to the minus t over RC. The voltage of the resistor as a function of time is V, the voltage of the battery, times e to the minus t over RC. The voltage across the capacitor as a function of time, well, unlike these first two terms that are decaying, the capacitor, its voltage is increasing, and it's given by V times 1 minus e to the negative t over RC, and the charge on the capacitor as a function of time is C times V, times 1 minus e to the negative t over RC. So what you can see is, as charging progresses, the voltage of the battery is constant. The decreasing current means that the voltage over the resistor drops. The increasing charge on the capacitor means the voltage across the capacitor increases. At t equals 0, there's no charge on the capacitor, which means there's no voltage drop across the capacitor. The current is at its maximum, as is the voltage across the resistor. It's equal to the voltage of the battery. As t approaches infinity, on the other hand, well, now that means that our capacitor is fully charged, so the voltage drop across the capacitor is equal to the voltage of the battery. There's no voltage drop across the resistor because there's no current flowing through it.